Okay, in this video, I'm going to go over how to create lines of regression. Regression lines, also known as a line of best fit, based on whether it's a linear, quadratic, or exponential data. So in order to figure that out, let's first make us a table. So this is using Desmos. And if you have a TI-84, you can look at how to do a line of regression on your calculator. But we're virtual class here. We're going to do Desmos. So we go up here to the little plus and we create a table. All right, so here we're going to create our table of data. And let's say we're going to do, we'll start with a linear. So when we do this, 0, 1, 2, 3, let's just put some data there. And let's do like -7, -3, -1, 2, 6, and let's go ahead and do like 8. Okay, so if we look at this data on the graph, that looks like it's linear, right? For the most part, that's linear. That's a straight line for the most part. It's close to that. So we believe at that point, a line of best fit would be a linear line. So we can do that in Desmos, and it will figure out what the line is for us. So if we click down here, and normally for a line, it's y equals mx plus b, right? That's the standard form that we could use for a line. To get a line of regression, we're going to do y1, and the reason we're doing the 1 is our data uses x1 and y1. All right, so we're going to say y1, and instead of using the equal sign, we're going to use this little tilde. It's above, it's next to the 1 over on the left side of your keyboard. It's a shift character. Use that instead of the equal, and that tells Desmos we want a regression line, not an equals. This is a regression line. Okay, so it's mx plus b, but we're doing mx1, remember, because we're using x1 plus b. Okay, now you notice it put a line on our graph, and that line is pretty good. That's pretty much the average of all this. Some of the points are a little bit above the line. Some of them are a little bit below the line, but that is the line of best fit. That's the line that most approximates our data. And you see over here, it's got this R figure. The R is very, very close to 1. If it's between 0.8 and 1, that's a pretty accurate line for the data we have. Now, what Desmos gives us right here is our M and our B. Mx plus B, our M is 3, so this line has a slope of 3, and our y-intercept is that negative 0.66666 repeating. All right, so this means we can write the line of best fit as y equals 3x minus 0.667. We'll go 3 decimals here. We'll make it 3 decimals, go to the thousandths. So it's y equals 3x minus 0.667. And that is the line of best fit for our data. So that's not too hard. Let's look at some data perhaps that is quadratic instead of being linear. So again, let's make ourselves, let's go -2, -1, 0, 1, 2, 3, maybe 4, 5. I'll just do a bunch of data points here. And let's say this is -2 is going to be 5 and 1 and 0 and 1 and 4 and 9 and 16, 25. All right, when we look at these points that we have, see, that looks quadratic. It looks like a parabola forming there. So if we want to know what is the parabola that best fits the points that we have, all right, so the standard form of a quadratic equation is y equals ax squared plus bx plus c, all right? That's the standard form. So we're going to base that same thing, y1, again, because our table uses x1, y1. And again, instead of the equal sign, we're going to use a little tilde sign, a x1 squared, right, plus bx1 plus c. ax1 squared plus bx1 plus c. And Desmos creates our line of best fit. And you see it almost perfectly goes. So that point's just a little bit off there at the -2. That point's off a little bit. It's really close, but that is the quadratic line that most approximates the data from our table. And you see the R squared number for the quadratic is really close to 1. So that tells us that this is a really good line. And as we can see, it's a really good line. It goes through most of our points. But here's our A, B, and C. So this is the A, B, and C we would use for our equation. If we're going to write the equation of that quadratic, we would say y equals 1.04, and we'd round up to a 2. Again, going 3 decimals. 1.042x squared minus 0.208x plus 0.125. So that's the A, B, and C that we would plug in to our standard quadratic equation. All right, one more I want to show you, and that is if we have an exponential. So let's look at an exponential table, and right there we'll create it, and let's do 0, 1, 2, 3. That's enough points in it. So if we have 3, 5, 11, 29. See, the 29 is way up there. See, that's one that's going up really quick. That looks exponential to us. So let's write. Now, the standard exponential equation is y equals a times b to the x, right? Or just b to the x. But a, there's usually a coefficient in front of the b. The b is usually the rate that the equation is changing. And x is the exponent in an exponential equation, right? So let's write that for a line of regression. The y1, again, no equal sign, right? We're using the regression symbol for Desmos. And we're going to say AB raised to the power of x1. There we go. Here's the line. Now, this one's a little high, but it's really close. The rest of them fit really nice. So anytime you have a line of best fit, you most always have outliers, things that are just a little bit off the line, but they're close enough for that line to represent. And that's what we have there. This point there, it's just a little bit off of our line. That's the 0.03. It's not even close enough for it to say that. Yeah, 0.3 right there. It's just a little bit off. But the other ones are really close. See, that one's off a little bit also. That one's off just a little bit, but that's pretty close. So here's our A and B down here that we would use to write our equation. So we'd say y equals 1.938 parentheses, then the B, 2.459, close your parentheses, to the power of x. And that would be our line of best fit for an exponential table, for an exponential data. So basically we just have to put our table, put our points on here, make our table, look at the information we have, and does it look linear? Does it look quadratic? Does it look like it is exponential? And then just try to see what fits. You know, and we could say, well, maybe I thought this was exponential. So if quadratic instead of exponential. So if we said ax1 squared plus bx1 plus c, well, it kind of models quadratic. Now, we don't have any information to the left of the 0 to see, does it continue down like it's exponential, or does it go back up? We don't have anything that bounces back up, so that kind of makes us think this is more of an exponential. And then when we compare that, the 0.9924, that's pretty good. It kind of models quadratic. It could be either way. This one's a little bit better fit with the 9959. So you look at your data, you figure out which one works best, and make your line of best fit.
Let's get out of here. Word to your multiples. Math, baby. We're learning math, baby.